Hi class, in this example we're going to go over problem 5. Now notice that problem 5 happens to be, well, a quadratic equation, so it's going to be defined everywhere. So the first part of the problem that we're going to acknowledge is the domain of f of x. In this case, you have from negative infinity to positive infinity. So therefore, the intermediate value theorem, provided that it changes sign, it's going to have at least a 0 technically anywhere in space. Here, we're limiting the interval from 0 to 4. So when we evaluate 0, we're just going to actually get the y-intercept of negative 12. So let me just evaluate. This will be 4 times 0 squared minus 3 times 0 minus 12. And this is equal to negative 12. What we're looking for here is the change in sign. And then at the values of 4, we're definitely going to have a large value. So I just want you to plug it in, and then you can use the calculator. So this will be 4 squared minus 3 times 4 minus the values of 12. Please take a second and evaluate. I'm getting that this one is a total of 40. So good news. We have technically a function that happens to be continuous. In the interval from 0 to 4, it changes from a negative to a positive. That means that there has to be at least a 0 in that interval by the intermediate value theorem. Remember that the basic idea, and I actually have the graph here, is that if you have a continuous function, in this case, we're looking at an interval from 0 to 4. If the function is continuous and you get a negative value and then technically a positive value somewhere out here, in this case it's at 4, so it's outside of the screen, there has to be at least a 0. So for these problems, we need a sentence where you include the following, and in this case the function has to be continuous. F of 0, we're getting that this is negative 12. Let me put it in blue. So negative 12, f of 4 is equal to 40. Then by the intermediate value theorem, there's at least one root or 1 0 on the interval from 0 to 4. That's actually it for this portion. On part B, all I want is a basic sketch. Not all of the problems that you see in this topic are going to be easy parabolas. So some of them, you're only going to be able to see a portion of them. So all I want is on any sketch, just the basic sketch and at least one coordinate point. So I'm just going to say that this is negative 12. You do have technology, so you'll be able to see that, well, the vertex, it's below to the right, and then it goes in this direction. So as long as you have one coordinate point, that would be fine. And here, well, one easy coordinate point to spot is the y-intercept, or 0, negative 12. And then all I want is a sketch of our function that it's going in this direction. Oh, I couldn't fix it. I think that's staying. And that's pretty much it. In this case, it's a little bit harder to see, but your y-intercept is 0, negative 12. So that's the coordinate point that I'm displaying. There's obviously more, but one is sufficient. The last portion of it is to final roots of f of x. So in this case, we're going to actually solve the following equation. So we want to know where f of x is equal to 0. Or another way of viewing it is we're going to be finding the roots. And they want them as coordinate points. So our actual function is 4x squared minus 3x minus 12. So 4x squared minus 3x minus 12, and this is equal to 0. So in this case, It doesn't seem that it's going to be factorable, so we're going to be using the quadratic formula. Make sure to add the quadratic formula to your formula package. So x is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. And for this problem, we have that a is equal to 4, b is equal to negative 3, and c is equal to negative 12. So as we apply the quadratic formula, we're looking at x is equal to, in this case, negative 3 plus or minus the square root of, actually, let me write first the whole formula. So x is equal to negative b plus or minus the square root of b squared minus 4ac divided by the values of 2a. And now let me plug in the constants. So x is equal to negative 3 plus or minus the square root of negative 3 squared minus 4 times the values of 4 times the values of negative 12 all over 2 times a, which is equal to 4. So this is equivalent to technically 3 plus or minus the square root of 9 plus, and let me just multiply that value. So we're looking at 4 times 4 times the values of 12, 192. So plus the values of 9, 201 divided by 8. So let me continue simplifying this one, since it looks like it's going to be a little bit messy. So x is equal to 3 plus or minus the square root of 201 divided by 8. I don't think we're going to be able to go further with this one with the 201. At this point, let me separate them. So the solutions are going to be x is equal to 3 plus the square root of 201 divided by 8, or x is equal to 3 minus the square root of 201 divided by 8, which are going to give us decimal approximations. Let me evaluate these. So I'm getting that this one is 2.147, or the negative of it. X is equal to negative 1.39. I'll go to 7. They do want these as coordinate points. So I do want to see exact values, and then in this case, exact values, and then decimal approximations are fine. But let me just compare with the graph. So we're looking at negative 1.39, which is technically this one. And then the other one is 2.147. So algebraically, we actually found both of the roots. This one worked out nicely. And they want the solutions as x-intercepts. So let me just verify. So the actual solutions are going to be technically 3 plus the square root of 201 divided by 8, 0, which is approximately 2.147, 0, or 3 minus the square root of 201 divided by 8, 0, which it came out to be negative 1.397, 0. Same idea as before. We technically want to express them as exact values and then decimal approximations. That's actually it for part C. Remember that the important part on the intermediate value theorem is that as long as we have a function that is continuous on an interval, in this case, we were only looking at 0 to 4. And if your function changes sign from, in this case, negative to positive, or any of those negative to positive would be fine, then there's at least a root. So here with this one, we're able to find the root algebraically. Also, please ensure that you add to your formula packet the formula for the quadratic formula. It's going to show up for a couple of the problems. That's actually it for this problem.